So we're going to have a look at the roots of complex numbers. To keep it simple, we'll look at ones with a mod of 1. But we do know with all complex numbers, if you square a number, you'll be doubling the argument. If you cube a number, then you'll be tripling the argument, and so on. And going backwards, if you cube root, then we're looking at a third of the argument. And if you square root, you're looking at half the argument. But instead of moving in a spiral outwards, we're going to keep it the same distance from the origin by having a mod of 1. Now, what I mean is we'll have things like z cubed equals 1, or z cubed equals minus 1, or I or minus I, and start from there. So because the cube roots, or square roots, or fourth roots are evenly spaced around the complex plane, your roots are going to form regular polygons. The regular polygon with 3 sides is called an equilateral triangle, and the regular polygon with 4 sides is called a square. But then we'll have a regular pentagon, or a regular hexagon, or a regular heptagon, or a regular octagon, or a regular nonagon, or a regular decagon. But that word regular is important, meaning not just that all the sides are the same, but all the angles are the same inside them as well. And we're looking at a lot of symmetry there in those shapes. So let's get started with z cubed equals 1. So z cubed equals 1 is also known as z cubed minus 1 equals 0. Now, what we know about this guy here from our Year 10 work is that the solution that we know of that's real is the number 1. So we can start with that particular solution, the number 1, and then we can work out the others because they're evenly spaced around the complex plane. So if we pop in the number 1 here, this is cis of 0, but it's the number 1 on the real axis. This is the imaginary axis, and this is the real axis here. So if we pop in the number 1, we only have 2 more roots to cover, and they've got to fit around that complex plane, around the 2 pi radians worth of angle. So 2 pi divided by 3, that's how they're spaced out. So if we go around 2 pi on 3 from here, we'll be out here. That angle around there is 2 pi on 3. And this will be cis 2 pi on 3. And of course, from here around 2 pi on 3 will be cis minus 2 pi on 3. And what we've made is an angle of 2 pi on 3 here, 2 pi on 3 here, and 2 pi on 3 in there. Each of those angles is 2 pi on 3. Another important thing to point out is that our complex roots occur in conjugate pairs because we know we've got real coefficients of our original polynomial. So that's z cubed equals minus 1. It is also interesting to point out that z cubed minus 1 equals 0 can be written as z minus 1 and then z squared plus z plus 1. The real root is 1, and the other roots are when you solve that equal to 0. So 2 solutions of z squared plus z plus 1 equals 0 would be this and this, because they send this set of brackets equal to 0 if this whole thing is equal to 0 by the null factor law. Non-real roots occurring in this real root, i.e. 1, sending this to 0. The next one I wanted to consider alongside of that would be, what about z cubed equals negative 1? We're going to get an equilateral triangle in the arrangement of the roots as well, just like we got an equilateral triangle here, but they're going to be placed in different places in the number plane. Well, already we know that that's the equation we've got, and we know from our Year 10 work that -1 cubed is -1, so -1 is going to send that to 0. So we can start by plotting here our first root from our knowledge of that and say cis of pi is our first root. It's a cube root that we're trying to find. It's a cubic, so they're going to be evenly spaced around the 2 pi, every 2 pi on 3 radians, which means they're going to be here, which is cis of pi on 3, and here, which is cis of minus pi on 3. Once again, to point out, the complex roots are occurring in conjugate pairs. To point out the symmetry, this is an equilateral triangle. And to point out that if I was to factorize that, I would get z plus 1, and over here I would get z squared minus z plus 1. So that's going to expand out to give me the z cubed plus 1. And this will give me my real root if I put that equal to 0, my real root of -1. And my complex roots will be solutions to this quadratic here. Another interesting thing to note before I erase this is that these two can be put together into one diagram. If I bring this diagram over here and pop it on top of this one, this will be cis of pi on 3 from over here. This will be cis of minus pi on 3 from here. And this will be cis of pi. We can see a lot of symmetry in that. But the interesting thing is, together, the roots of this and the roots of this combined give me the roots of z to the 6 minus 1 equals 0. Now that makes sense because z cubed minus 1 times z cubed plus 1, that's like a minus b, a plus b. So that'll be a squared minus b squared, which is z to the 6 minus 1. So these two factors are just z to the 6 minus 1 factorized. So the solutions of these, when this is put equal to 0, and the solutions when this is put equal to 0 are just going to be the solutions to z to the 6 minus 1 equals 0. Now, if I change this and look at the situation where z cubed equals I, or z cubed equals minus I, what's going to happen? Well, we won't necessarily have the complex roots occurring in conjugate pairs. Why? Because the original polynomials, they don't have real coefficients. So our complex roots don't have to occur in conjugate pairs. So let's have a look at this one. I mean, this says z cubed minus I equals 0, and this says z cubed plus I equals 0. And before we go any further, let's go over to the side here and work out what the combination looks like. Z cubed minus I times z cubed plus I. What does that look like? Well, if we expand that out in the same way as we did before, that's a minus b, a plus b, then that's a squared minus b squared. So that's z to the 6 minus 1, which is z to the 6 plus 1. So the combination of the previous ones was z to the 6 minus 1. The combination of this is going to be z to the 6 plus 1. Right, let's do them each individually. So where do you think that the solutions are going to lie for that one? They're not going to lie in the same place as they did for z cubed equals minus 1 or z cubed equals 1. But they are going to form equilateral triangles on the complex plane. Can you see a solution? Do you know a number that when you cube it, you'll get positive I? When you cube it, you'll get positive I. What about this number here? Negative I, which is cis of minus pi on 2. What happens when you cube negative I? Negative I times negative I times negative I. You can say negative times negative times negative will give you a negative, and I times I is negative 1 times I. You've got yourself negative I, so that'll end up being I, won't it? And I minus I is 0, or if you like, z cubed is I. So you can find one pretty easily by symmetry, if you like, knowing where to look. Okay, that being a solution, the other two have to be here and here for the reasons we explained before about symmetry, about them being evenly spaced around the complex plane at 2 pi and 3. So this will be cis of pi on 3, and this will be cis of 2 pi on 3. Is that correct? Does that give us 2 pi on 3 in this direction and 2 pi on 3 in this direction? And are these separated by 2 pi on 3? That's the first thing to ask. So in other words, is that 120 degrees there? Is that 120 degrees there? And is that 120 degrees there? The answer is no, that's not right. So that's only 90 degrees in there. Between 60 and 120 is only 60 degrees, sorry. We need 2 pi on 3. So where should we have plotted the points here? That's right, round here at cis pi on 6 and cis 5 pi on 6. Now that's going to be 120 degrees, 90 plus 30 to get up to pi on 6 is 30, and 90 plus 30. And that also makes sense because it's not going to be on the same solution set as the other one, which is the cubics. All right, so that's z cubed minus 1, z cubed minus I equals 0. And the solutions to z cubed plus I equals 0, no surprise, is cis pi on 2. And here, cis of minus pi on 6 and cis of minus 5 pi on 6. And it's no surprise, because we've worked it out already, but it's no surprise to be able to see that combining this one with this one, so just bringing the solutions across, we've got cis of minus pi on 6, we've got cis of minus 5 pi on 6, and we've got cis of pi on 2. If we put those two together, we're going to end up with z to the 6 plus 1. And they're evenly spaced around the complex plane. Between 30 and 90 is 60 degrees. In other words, that's pi on 3 separating those two, and pi on 6 plus pi on 6 is pi on 3, separating those things. So my scale's a little bit off. And that there is meant to be pi on 3 there as well. Pi on 3, pi on 3, pi on 3. Pi on 3 is 2 pi on 6. They're all separated by 2 pi on 6, and that's because the combined effect is the combined effect of the polynomial z to the 6 plus 1 equals 0. So you can see the equilateral triangles that have been made, but neither of these has a pair of complex roots that are conjugates because the original coefficients were complex, not real. All right, so let's step it up and have a look at forming a regular quadrilateral on the complex plane. So that would be z to the 4 equals 1. Or if you like, z to the 4 minus 1 equals 0. We know two solutions for that already. One, which is cis 0, and minus 1, which is cis of pi. And we know that they're evenly spaced around the complex plane, so it's pretty easy to figure out where the other solutions would be. If there's going to be two more solutions, wouldn't they have to be there and there? Complex solutions, they're occurring in a conjugate pair because the original had real coefficients. So that's I, and that's minus I down there. In other words, cis of minus pi on 2 and cis of pi on 2. Now, if I had z to the 4 equals minus 1, that's z to the 4 plus 1 equals 0. They're just going to be rotated so that we have no real solutions. We know there's no real solutions because you can't fourth root or square root of minus 1 in the real number system. And if there's no real solutions, but they have to be evenly spaced, and if the polynomial, the original polynomial, has real coefficients, they've got to occur in conjugate pairs, that limits it right down to where they have to be, right? They have to not be on this axis because no real solutions. They have to be symmetrical. Whatever's up here has to be exactly down here because they're conjugate pairs. And they have to be evenly spaced, which makes them have to be every 45 or pi on 4. So they're right smack bang in the middle there. So this is cis pi on 4. This is its conjugate, cis minus pi on 4. This is cis of minus 3 pi on 4. And this is cis of 3 pi on 4. Evenly spaced, conjugate pairs, etc., etc. And if I move these across to here, you can see also why it's so easy to see where these ones would be if you'd already graphed this one that's in black, because everything has to be evenly spaced if you're going to do the combination. And what is the polynomial that is the combination? Without having to expand it out, we know that z to the 4 minus 1 times z to the 4 plus 1 is going to end up being z to the 8 minus 1. So the solutions of each of these together make the solutions of z to the 8 minus 1. So what would the solutions of z to the 8 plus 1 be? What two polynomials combined would be the solutions to z to the 8 plus 1? And from our work with the cubic, that's what the answer would be. So let's graph the two regular quadrilaterals in terms of their roots. Z to the 4 equals I, or z to the 4 minus I equals 0. And z to the 4 equals minus I, or z to the 4 plus I equals 0 on the number plane, on the complex plane. As usual, that's the real, that's imaginary. So where do you think the solutions would lie? We have to have not complex conjugates, I guess, because it's not real coefficients here. We don't have real solutions, so it's going to be a little bit skewed the way our solutions work out. So the first solution will be one of the solutions of this. And there's 8 solutions of z to the 8 plus 1 that we need to distribute 4 to each one of these. So one of the solutions is going to be about there, cis of pi on 8, because we're looking at z to the 8 plus 1. And if that's cis of pi on 8, and if you space these out every 2 pi on 8, then this will be cis of pi on 8, cis of 3 pi on 8 over here for our other one. So if I were to combine them, they would be evenly spaced. Okay, so that's cis of pi on 8. We're going to come over here and have cis of minus 7 pi on 8. And of course, we can come over here and have cis of minus 3 pi on 8 for this one. Now these directly across from each other, because we've got ourselves a quadrilateral happening on the number plane. So these will be directly across from each other as well. And the other 2 solutions will be there and there. So what would they be? They're not conjugate pairs. Well, that's right. This one is cis of minus pi on 8, which is the one that's from here, but this one can't have a conjugate pair, so it must be over here. Right? This one can't have a conjugate pair, so it must be over here. This must be cis of 3 pi on 8, negative. And what's the final one over here? Cis of 7 pi on 8. So we've got 5, that's 4 pi on 8 apart. That's 4 pi on 8 apart. That's 4 pi on 8 apart. This I've got wrong. It's not 4 pi on 8 apart because there's 3 pi on 8 plus pi on 8. Oh yeah, that works. That works. I think that should be 5 pi on 8 to make them 4 pi on 8 apart. That should be 5 pi on 8 there. And that would mean this is 5 pi on 8. Just getting them to be 4 pi on 8 apart. That's pi on 2 because they're 90 degrees. So that's 90, that's 90, that's 90. That makes sense because those two, like you can't have conjugate pairs here, but those two match up. Those two match up. Those two match up. And those two match up. All right, I think I've got that one right now. So when we combine them together, they make z to the 8 plus 1. When we combine z to the 4 equals I and z to the 4 equals minus I. So we go every 2 pi on 8 apart. So this one here is cis 3 pi on 8. This one over here is cis minus 5 pi on 8. And we've got cis of minus pi on 8. And we've got cis of 7 pi on 8. Okay, so just put my dots where they should be. And this should form, if I'd drawn it to scale properly, the black one should form a square and the red one should form a square. And if you joined up going around, you should form a regular octagon in response to 7 to the 8 plus 1 equals 0, which is the combination of these two. So let's take it to the last step I want to have a look at the moment, and that's z to the 5. Let's have a look at what goes on for it. So z to the 5 equals 1, or in other words, z to the 5 minus 1 equals 0. From year 10, we already know one solution for that. Right? We want to turn this to a 1, so it's 1 minus 1 is 0, and we know that that's a solution. 1 minus 1 is 0. And we know they've got to be spaced evenly around the complex plane, so we need to fit the 5 solutions every 2 pi on 5. So this is 0, and we need to go 2 pi on 5, which is around about here, let's say. Cis 2 pi on 5. And then we go around to about here, cis 4 pi on 5. We go backwards to cis minus 2 pi on 5, and about to here to cis of minus 4 pi on 5, roughly. So that's roughly what the solutions are. Once again, now we're back to having a polynomial with real coefficients. We've got ourselves some conjugate pairs happening. We've got our real root by itself, but our complex roots are occurring in conjugate pairs because the original polynomial had real coefficients. And if we look at z to the 5 equals minus 1, in other words, z to the 5 plus 1 equals 0, we know an answer for that. We know that negative 1, or cis pi, to 5 plus 1 is 0. We know that from our year 10 work. And so we go and do the same thing. This time our solutions are there and there and there and there, which you can see is like a mirror type of that one. The two of these are very closely related. It's separated every 2 pi on 5. So this is at 3 pi on 5. This is cis minus 3 pi on 5, and I know that because it's a real coefficient, so they're complex roots. If they occur in conjugate pairs. And this is cis of pi on 5, and this is cis of minus pi on 5. And once again, if I put together the solutions to them, so if I pop cis of pi on 5 on there, cis of 3 pi on 5, cis of minus 3 pi on 5, and cis of minus pi on 5, and also cis of pi. Those 10 solutions there, if I'd drawn it accurately, would form a regular decagon, and they'd be the solutions to z to the 10 minus 1 equals 0, because z to the 5 minus 1 times z to the 5 plus 1 is the same as z to the 10 minus 1 equals 0. So the solution set to this and this combined is the solution set to z to the 10 minus 1 is 0. We could go on to draw the roots of z to the 5 equals I and minus I. So let's just have a look here. Just restart, I think. So z to the 5 equals I, or z to the 5 minus I equals 0. and z to the 5 equals minus I, or z to the 5 plus I equals 0. Once again, if I start over here, z to the 5 minus I times z to the 5 plus I is z to the 5 squared minus I squared, a minus b, a plus b. So it's z to the 10 minus 1, which is z to the 10 plus 1. So the combination of these will be the decagon made for z to the 10 plus 1, evenly spaced roots. Now, none of these will have conjugate pairs. So we're going to, first of all, sketch this one evenly spaced. This first one, our first answer is cis of pi on 2, which I'm going to write as 5 pi on 10. And the solution for this one over here is cis of minus 5 pi on 10, cis of minus pi on 2. Sort of reflective in a way. Now, this one's got cis of pi on 10. And because they can't occur in conjugate pairs, then the solution, minus pi on 10, the conjugate solution must be over on that one over there. Now, I'm just checking if I've got this the right way around, and I think I do. Yeah. Cis of minus 3 pi on 10 would be there, which means cis of 3 pi on 10 would be over there. Cis of, well, we have to go around to probably 9 pi on 10 over here. And then this one will have cis of minus 9 pi on 10. And there should be 5 solutions. 1, 2, 3, 4. So this would have to be 9, 8, about cis of minus 7 pi on 10, which would mean this one would be the one that has cis of 7 pi on 10. So they're evenly spaced every 2 pi on 5, but I was doing every 4 pi on 10. So as long as I had one, I just go for plus 4 pi on 10, plus 4 pi on 10, plus 4 pi on 10 to get them. And they would probably fill the gaps of the bigger polynomial again to the 20 if you put all the other ones in that we did in the previous one for z to the 10 minus 1 equals 0. So they're forming regular pentagons. And finally, z to the 6 equaling 1, which is z to the 6 minus 1 equals 0, we know a solution for straight away, and that is here at cis 0, because 1 minus 1 is 0. This one has to be evenly spaced every pi on 3, 2 pi on 6. So it's quite easy. You've got pi on 3, it's about there. So this will all be nice and symmetrical, especially with the cis of minus pi on 3, cis of pi on 3, because it's a real polynomial. We've got our conjugate pairs happening. Cis of minus 2 pi on 3, cis of 2 pi on 3, and cis of pi here. So that's our regular hexagon that's been formed here out of the roots of z to the 6 minus 1. And without having to draw the other one, z to the 6 plus 1 equals 0. We know they're going to be here, 1, 2, They're not going to be. They're not going to. Yes, they are going to occur in conjugate pairs because that's a real polynomial. So those two will go together, which means those two will go together, and we've got to go there and there, which is going to give us a regular hexagon as well. These are just rotations of each other, these two polynomials, and forming z to the 12 minus 1 in combination. Now, if I just pick up on this one here and make it all out of 12 out of interest, this is 4 pi on 12 and 2 pi on 3 is 8 pi on 12, and this is minus 4 pi on 12, and this is minus 8 pi on 12, and this is 12 pi on 12. So if we do build up this polynomial out of 12, and this one was the one that was halfway in between there, so this will be cis of 2 pi on 12 and cis of minus 2 pi on 12, and this was cis of minus 6 pi on 12 and cis of 6 pi on 12 and cis of 10 pi on 12, and this one here is cis of minus 10 pi on 12. Just get another colour here, because of those two polynomials put together, we've said makes z to the 12 minus 1. But what can we make of all these dots that are halfway in between here? What can we make of all those dots there? Are there some of those dots that we could form a regular hexagon with? For example, could we start with pi on 12 here and skip that one and go to that one and skip that one and go to that one and skip that one and go to that one and skip that one and go to that one and skip that one and go to that one? If you look at the ones that have a cross, they will also make a regular hexagon. What polynomial would they be the solution of? Just get a black pen to draw the regular polynomial, the regular hexagon we're talking about. There, 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 and there. This diagram is getting complicated, but we're starting at cis pi on 12, and we're missing 2 pi on 12, 3 pi on 12, 4 pi on 12, and our next one is cis 5 pi on 12. So these are 4 pi on 12 apart still, right? Our next one is cis 9 pi on 12. Going backwards here, this one is cis negative 3 pi on 12. This one that I've crossed here is cis of negative 7 pi on 12. And this one I've crossed here is cis, I'll just get rid of this, cis of negative 11 pi on 12, I think, because 10 was that green one there. What are they the solutions to? And the answer is that these ones here are all the solutions to z to the 6 minus I equals 0, or z to the 6 equals I. And complicated as the diagram is, the other dots that are there will be the solutions to z to the 6 equals minus I, or z to the 6 plus I equals 0. And those 24 dots will form the solution to you know what. So that's just a bit of a discussion about regular polygons on the complex plane.